And this is rather strong, and you need a lot of regularity in order to apply these kind of and to work with this kind of distance. So just to give a hint why, maybe we'll talk later about different kind of distances. Okay, so there was one tool for studying these kind of problems, and these are strongly uniform stopping times. And they are associated to the shuffling process. You start in a perfect order, you just apply this kind of shuffling, and then it is a random time such that when you evaluate the process at a certain time k, so if this random time is hit at a time k and you evaluate the process there, then you are in a uniform distribution. Okay, so of course this sounds very crazy that this kind of things should exist, but they do, and there are very concrete examples, and we will see briefly one of them. And why are they good? Because first of all, they are good bounds on these kind of objects which we have here, which we want to estimate. They are easy to manipulate because there will be probability estimates which we can get there, and you can construct them in many examples which have sufficient symmetry in the system. So there's a way how to construct them more or less constructively. Okay, so here is the dilemma. So it says just if you have this kind of shuffling process, then the probability of t not having been reached is a good estimate, an upper bound for the probability of the distance after k shuffles from the uniform distribution. So here is the proof. The proof is very simple. You just have the probability here. So, and you can always intersect with t not having passed yet, and t having the values before. Then here you can write it as a conditional distribution. And this conditional distribution is just what we have here. So there's a uniform distribution, U of S. So the good thing is this is uniform for everybody. So this does not depend on J anymore. You can put this out. You can sum over here and you have the probability of t less or equal than k. So this is 1 over minus what we have here. We can just pull it out and reorder it. And what we get is, so if this is for 1s, you just sum over all of them. We get this kind of estimate. Of course, I don't expect you to follow every of the step, but I wanted to give you an intuition that this is rather elementary and it just uses more or less the definitions. So one special shuffling technique where this was applied is the riffle shuffle. It's okay, inspired, of course, by some Las Vegas movies. You have some, so you have a deck of cards, you divide it at random into 2 parts, and then you just mix the 2 sub decks in a random fashion into each other. So you can imagine this, you just have, if you have 5 cards, you have a random number, you split them into 2, and then you mix them in a random order where you respect the relative order of each of them. Okay, and therefore each t there are n over t ways to interleave the 2 sets. Okay, this is rather elementary. So, but of course, it's not clear in advance which kind of permutation you apply or which you assign to each of those riffle shuffle permutations. But the most elegant one and the most simple one in some sense, which you can apply is the one which was applied by Diaconis. And it says just if you're not on the riffle shuffle, you have 0, and you apply to each of the permutation 1 over 2 to the n. And so if you can see here, if you put some t, so for each subset, you can have a, for each subset which you put there, it can come from exactly 1 possibility, and then you can see that there are n plus 1 over 2 to the n possibilities. So this is just counting the possibilities of getting these kind of subsets. And this is some kind of uniform distribution what you have here. So, but if you do this, you have a lot of good properties. One of the good properties is that you can also define an inverse riffle, because inverse riffle just means that you have a set, you assign some kind of 0s and 1s to the elements. So you pick some strictly random subset, and you call it 1s. and the others zeros, and you just separate them, keeping the relative order, and put the whites on top and the blacks below. So the zeros on top and the ones below, and then you put them here. And there's a good property that says that the inverse riffle and the original riffle are just have this kind of relation. So this means that in particular you can use the difference between the original riffle and the inverse riffle to the uniform distribution is equal in the total variation distance. So, and here is the theorem. So the riffle shuffle applied k times has this kind of upper bound, and this kind of upper bound is stronger than this just exponential, this kind of exponential convergence. Just maybe saying one thing. So the total variation is a number between 0 and 1, where 1 is the largest distance possible and 0 is the smallest distance possible. So of course it's a distance, but this of course will play a role in the second part of the talk, and you can see that for n larger and larger, this means larger and larger decks of cards, this kind of convergence gets rougher and rougher. Really, it's some kind of sharp decline. So how can you see this? First of all, you pass from the riffles to the inverse riffles. This is once again the same picture. So what was the inverse riffle? You just this purely at random, you pick subsets and you divide them up and down respecting the relative order. And you can do this repeatedly until you have zeros and ones, and the zeros and ones are all different. So if you assign zeros and ones and you keep them and you apply them once, and then you have for the first row, you once again have a reshuffling. No, but still in this here, you have still 0, 1, 0, 1, which is the same. But once you apply it more, so at a random shuffle, you get, for instance, this kind of sequence, and this would be the first moments when all binaries are different, and this is a strongly uniform time. So, and the good thing is that here you just have 2 to the k boxes or 2 to the t boxes, and if you do this, you can calculate the birthday problem, which is associated. You have 2 to the k boxes. These are the birthdays, and the question is that what is the probability that all of them are different? And doing this, you get the upper bound, which we have on the right-hand side of the statement. So, okay, this is of course not a detailed proof. You have to, more arguments are needed, but in the end, this is the basic road proving this kind of theorem. And this is stronger than just exponential. It just, if you do this for 52 cards, then it is shown in the book by Eigen and Ziegler how these numbers fall. So first of all, they are almost constant, and then suddenly you have a breakdown to numbers very close. First of all, smaller than 1/2, and with 7, you have for 52 cards, you have you need 7 of these kind of riffle shuffles in order to get a number which is, as Diaconis claims, sufficiently close to 0 for practical purposes. Okay, maybe I would have chosen 8, but I'm not a magician. All right, so you see there are ways to do this, and this is rather special. So you cannot do this in general. You have a lot of symmetries involved, and so far there are no good criteria saying that something like this kind of strong, sharp decline occurs. You cannot really give good criteria. So there have been conjectures, but nevertheless, they haven't materialized so far. Okay, so now let me have a look at the time. This is good. So now we have seen that there has been some kind of stochastic process, which has an invariant distribution. And there has been a parameter, and this parameter was n, the number of cards, of the deck size. And what is cutoff thermalization or cutoff? The cutoff phenomenon is just when you not only have upper bounds, but also lower bounds. This means that you have a very precise estimate from above and from below of this kind of distance, not only upper bounds and not only exponential, but in a very strong and very determined way. And this is a property which gets steeper and steeper for some kind of parameter. So, okay, maybe one word about why I say cutoff thermalization and not the cutoff phenomenon, as, for example, Diaconi said. In physics, these kind of properties are known as thermalization. And if you leave out the word cutoff, nobody in the mathematics community will recognize it. If you leave out thermalization, nobody in the physics community will recognize it. So we've chosen to put cutoff thermalization in order to have, hopefully, both audiences. Okay, cutoff thermalization is a property which is asymptotic in some kind of parameter. This parameter in our case was n, or maybe 1 over n. This may be easier because you don't want to have limits to infinity, but to 0. There is always some kind of cutoff time scale, which we did not calculate here for the riffle shuffle. But nevertheless, these are times which tend to to infinity if the parameter tends to 0. And what you have is you see the sharp decline. So if you are strictly slower than the cutoff time scale, then you are in values close to 1. If you are strictly faster than so for example, twice as fast as the cutoff time scale, then you are in values close to 1. And of course, this decline should not become slowly, but it should rather happen in a way which allows to quantify it, which allows to give it, so it's traveling to infinity, but its size is in fact smaller. So it's not as small as the whole time itself. So you have a distinct window where this kind of phenomenon happens. Okay, more precisely, still more. So this is the first idea. So if you are faster than the cutoff time, then the distance gets small. If you're slower, then you remain close to 1. Of course, this is something which depends. So here, so how it's written there depends very much on that we are working with the total variation. In fact, the total variation, as I mentioned, has some disadvantages in continuous time. It needs quite some regularity in order to be treated, in a sufficiently smooth way. So it's not an easy object. And one of the main problems of the total variation is it's not continuous under small discrete perturbations. So if you have small discrete perturbations, you can see it's not affected. So what we get here is a more precise definition. It tells us it's an asymptotic threshold property. I changed the name of A to epsilon for convenience because in what we wrote it was epsilon, and because I wanted to steal this kind of picture where it was A. Okay, so no problem with this. So what do we have? We have a stochastic process. Typically, it's a Markov process because the Markov theory where you have invariant measures is very well developed, but it does not have to be. It could be something different too. So it can be, for example, some kind of fractional things are still possible. Then we have a renormalized family of distances. Okay, if you apply the total variation, you don't have to renormalize anything. I will tell you why not. If you apply something different, as for example, the Wasserstein distance, then we will have to do something and we have to renormalize. And these kind of distances are distances on between probability measures on the state space where our process lives. And in the weakest form, it says we have this kind of cutoff timescale. We have a family of invariant distributions. Of course, they depend heavily on, for example, how many cards determines how big the uniform distribution is. It's all a uniform distribution, but depends on how big the space is. It's different. And then you have this fall off of infinite zero collapse. Okay, this is just rewriting what we have here. Here I changed the 1 to C infinity, and C infinity just tells us that, for example, if you have the Wasserstein distance, then the largest distance between two distributions is not 1, but infinity. Okay, so you have some kind of what is the largest distance between two objects between two distributions over the state space, and it turns out to be different from 1, so it turned out to be infinity in the case of the Wasserstein distance. All right, so what do we have here? We have a process, a family of processes, which are parametrized. We have invariant distributions, which are also, of course, following the parameter. And we have a renormalized family of distances in which you measure them. And then you have a time scale, which may depend, for example, on the initial value, which is something, of course, Diaconis wanted to avoid at all events, because you don't want to have some kind of preferable starting values. But in general, things will depend on initial values, where you can get some kind of sharp zero infinity or C infinity zero collapse. All right, so this is what we are looking at. And the object we're looking at is the Ornstein-Uhlenbeck system. So the Ornstein-Uhlenbeck process is an object like this. So what do we have here? So the first thing is a stochastic differential equation. Forgive me, we will read in a minute the integral equation, which is much easier. So the stochastic differential equation, it tells us that the increment of, or the dx is just linear minus q, and q will be a matrix. It will be stable, so minus q will be stable. It will have negative real parts, and we have some kind of perturbation. This perturbation will be something like here, Brownian motion, you have Levy flights, the mystic drift can be even there, so linear functions is possible. And for example, a compound Poisson process. Typically at this point, I would just give an introduction to all the noises and why that. At this point, I won't, because our results are just telling us that it does not really matter what is there. Okay, so you can think of a compound Poisson process. This means you have an IID family of increments, and you have waiting times, you jump waiting times. This means your process is a process which is just flipping around in a certain way. It has stationary increments. It's a Levy process. Stationary increments, it has independent increments, and it's not absolutely crazy. So it has always some kind of good behavior. You can also think of the Brownian motion. You have some kind of Brownian motion. And in order to think about this, you can also see this as some kind of integral equation. Here you have this kind of process we are talking about. It's some kind of irregular continuous random functions which come here. And we have this kind of integral equation where we have some forcing, which with some negative feedback forcing. Okay, so these are the objects we will have a look at, and our parameter, our cutoff parameter, will be epsilon. So for every epsilon, we will see that there are invariant measures, and we want to see some kind of cutoff phenomenon for small epsilon. All right, so the first thing when we look at this is that we rewrite the solutions of this. We can write this implicitly, but the good thing is, since it's linear, you can write it explicitly. And of course, if you think that you have some kind of, if you had some kind of continuous function, you would think of a convolution here, and this is precisely what happens. You have some kind of convolution. The only thing is that you have to write it as a stochastic convolution. So our solution has two parts. One is the linear part applied to the initial value, which typically in ergodic theory just goes away. And then you have some small perturbation, which very often does the game. In our case, we will see that the linear part in effect is the main player here. Okay, so these are the objects. We have some kind of good explicit representation. These are, okay, these are convolutions, but nevertheless, they are not strange. Here we have a stochastic with a matrix exponential. So it's defined in the usual way. You have the sum of the q to the k divided by k factorial. All right, so the first thing we assume is asymptotically exponential stability. This means we have q, which has real parts which are all positive, such that minus Q has all real parts negative. Of course, this is something rather well known. So you have some kind of stable semi-group, which is there, and it's very classical to derive this kind of upper bounds. Okay, upper bounds are good, but as we have seen, they are not sufficient. Upper bounds are in some sense only give a very incomplete picture of what really happens. Instead, we have a very, very precise asymptotic behavior on the stochastic, on the matrix exponential. If you look at e to the minus qt times x, then you can rewrite it, just here it is, you can rewrite it as, first of all, this kind of exponential, you have some polynomial part, and then you have something which is oscillating. So what do we have? We have some essential rate, which is the smallest real part of the which applies. You have multiplicities. You have number of blocks, and we have the longest length of the number of the size of the Jordan matrix blocks. You have angles. So you can think of the argument of the generalized eigenvalues. And you have linearly independent vectors, which are the generalized eigenvectors, so to say, of Q. And then you can write it down very precisely what the long-term behavior is. So you have some kind of exponential decay. You have the polynomial, which corresponds to the largest block of the largest size. Everything depends on the initial value. So everything depends on to which vector you apply this. So you have some x here, and you apply this to some of the vectors, and then it depends on which kind of components of x fall into certain subspaces, and if they are, some of them are skipped, so you are in some certain subspace, then some of the terms are skipped, and then you have some kind of rotational parts, and these rotational parts can be nasty. So they can be really some kind of e to the it theta to apply to these complex vectors. These vectors always come in pairs of complex conjugate vectors, but nevertheless they can be very complicated. So, but this is the essential picture, and with this in mind, we can continue, and we can see that we can reduce parts or the essential parts of the dynamics to this kind of behavior. All right. Okay, so what do we assume? We assume that L has some kind of moment. Okay, here for convenience, I take first moments. It can be anything. It can be some kind of positive moments. Of course, then the Wasserstein, with which we will work, is not very nicely defined, but still you can do anything. You can carry out everything also for p smaller than 1. Okay. In this case, if we have this, then there's a unique invariant measure, and it's very classical. Then you have the convergence in distribution. Once again, this here, the first term, this is the representation of the solution. This here is deterministic, and this here is the stochastic part. And the good thing is that the stochastic part is very special. It's not somehow the epsilon is not cooked in a very strange way into this, but it's there as a prefactor of this kind of stochastic convolution. So we know that the linear part tends to 0 due to the stability. So, and for t to infinity, and this object tends to infinity. So if t tends to infinity, it tends to a random vector, so to say. And you can see that these things converge, first of all in distribution and later on in Wasserstein. And you have an explicit parameterization of the invariant measure. All right, so as I said in the first example of the card shuffling, a total variation is nice on finite spaces, but it's hell in continuous space. And there have been already, has been work on the same kind of problem with the total variation by my co-authors, by Gerardo Barrera in Helsinki, and by Juan Carlos Pardo from the CIMAT in Mexico. And they've been working on this, and they have to assume a lot of things if you apply some kind of Levy processes. So if you don't have sufficient smoothing in your semi-groups, things get really bad. So what you wanted to do is to get results which are somehow generic, and the good generic distance is the Wasserstein distance, because in many ways it's convenient. In particular, it also implies the convergence of moments, which are for people who apply this in physics very important. All right, so what is the Wasserstein distance? The Wasserstein distance is nothing else but the LP distance, where you take the infimum, so you optimize over all joint distributions which have mu1 and mu2, the two measures which you compare, as marginals. So, okay, my students from probability theory, they already know that the joint probability distributions are not defined, so are not uniquely determined, so you can optimize over them. So one thing is you can, under very certain conditions, you can find explicit formulas, for example, in one dimension, excluding p equal to 1. You can do this, but this is a very exceptional, and typically you cannot. So this is a distance which is given in an abstract way. It's not hard, it's not difficult, it's not easy to evaluate. It's, however, you can give a lot of very favorable properties of it. Okay, the first property is it is a distance. Okay, this is something which should be clear. It is translation invariant with respect to deterministic vectors, which is also something which you can find, for example, for the total variation. It's homogeneous since it comes from kind of norms. You can always factor out. You can always factor out constants, and these constants is just with a norm to the 1. If you look at this for the total variation, this looks very different. It's the power 0. So the total variation is really invariant under multiples, which is something totally counterintuitive. And this is why you don't need some kind of renormalization, which will come out in a minute. And we have something which is the good thing, which we discovered. It's something rather natural, but it's not written down so we haven't found good sources of it. We had to prove it our own. It just tells us that if you look at the Wasserstein distance of some kind of distribution, of some kind of random vector, and you shift it, then the shifted distribution is just the norm itself. Okay, so this is something, yeah, you would expect this is somehow normal. However, it absolutely fails for the total variation. And this is something which we will take a lot of advantage, because it will tell us that this O infinity, this kind of limiting distribution, will just disappear. We can see that things which for the total variation are very, very tedious, they remain abstract, you don't have parameterizations, etc. You have to simulate, can be written down explicitly, because this kind of, here, if you measure this kind of distance, it does not depend on the distribution. Okay, you don't have to know something like invariant distributions, which are very hard to get. Okay, of course you get so the Wasserstein distance is of course the optimization of any kind of coupling. So you can bound it by any coupling you would like. So, and the good thing, so one of the important things just to see is that the convergence in the Wasserstein distance is the same as convergence distribution plus the convergence of the moments. Okay, so this is something, of course, in finite spaces, it almost never matters. Nevertheless, in continuous spaces, it is important, especially if you have processes which do not have certain moments, for example, alpha stable processes. Okay, so using these kind of properties, we can show that we not only have that OT converges to O infinity in the weak sense, but also with respect to Wasserstein. The only thing is you have to show that the moments converge. And this, by the shape of x epsilon, And mu epsilon, which is just epsilon times O infinity, we can show that the Wasserstein distance, the current state and the invariant distribution tend to the distance of this in Wasserstein distance tends to 0. This thing is not easy actually for the total variation distance. We worked quite hard on for the total variation distance to have some kind of deterministic vector here. Things are not well behaved. All right, so now what are we doing and why should it work? So you remember these kind of properties. I will just hope to recall them all. First of all, if we have this kind of distance, then this is just the shape of the solution which we had. This is the shape of the invariant measure which we had. And so what we do is we just plug in some kind of deterministic vector, which we can because we have the triangle inequality. So, and the good thing is that the second term, which we have here, just does not depend due to the shift linearity, which we have there in red. So it does not depend on this O infinity, while in other distances it does depend. So we can write it down. It is nothing but the absolute value or the norm of this matrix exponential, or this evaluation of the matrix exponential on the initial value. And what we have here is we have the prefactor epsilon. It just can be by the homogeneity pulled out. And we get that the Wasserstein distance of x epsilon to mu epsilon has an upper bound, which is just given by epsilon times the distance between the stochastic convolution at a finite time to the stochastic convolution to infinite time. Conversely, you can do the same thing. You apply this red property, this shift linearity, you get this, you apply the triangle inequality, and once again, you can just cancel out by the shift invariance these deterministic vectors here, and the same, thing, you can, and once again, you can reproduce, this is the shape of x epsilon, and this is the shape of mu epsilon. So what you get is that if you just put these things together, we have that the Wasserstein distance between the current state and the equilibrium measure divided by epsilon has an upper and a lower bound of the same shape. It is this matrix exponential, and then we have errors of this shape. And the good thing is that the error of the WOT tending to O infinity does not depend on any kind of epsilon. So remember, we had some epsilon as an original problem, and then we get some kind of expression in epsilon and t. And here we have no play in epsilon. So this is something whenever t tends to infinity, this term will tend to 0. So if there is some kind of cutoff or abrupt convergence, it should be found directly here. It should be found in the red parts. So this means there is a play between some kind of t epsilon and epsilon itself. All right. So there should be a play such that at a certain time you're far and then suddenly you just collapse. And this is the basic idea. So recall that we had this kind of asymptotic expansion. And okay, these kind of things are nice, but this oscillating term can be really nasty. And so in general, if this thing happens to have some kind of conversion, if this matrix exponential should converge, then we need some kind of convergence of this term. In general, it does not converge, and generically it does not converge. However, we can identify when it does. And this is good, because we can do this in terms which are well known to physicists, and these are normal growth patterns. So when do we have that, that this kind of function is, well, first of all, here it is constant, but when do we have a kind of a convergence? So what do we have? We have nu with some kind of moment. We have q satisfying the stability hypothesis. And then we have that these kind of limiting points, so the accumulation points for t to infinity of this kind of oscillating terms, if the norm of these points is constant, this means they are contained in a sphere, everything should be right. What is right? Right means that we have actually not only upper bounds and lower bounds, but we have actually convergence. So what do we have? Then we have the limit of P, so the W, so the Wasserstein distance in P between the current state evaluated at some kind of cutoff time scale plus some kind of constant. To the invariant distribution divided by epsilon converges, and this function, which in the case, for example, of the total variation is horrible. It's not easy. It's not nice. It has to be simulated, and it's given just as the distance between some shifted invariant distribution, has this explicit shape. It is nothing but, in the end, an exponential function. Okay, this exponential function has some kind of ornaments, but these ornaments are given in spectral terms. Still, these V's are strange. Of course, you can just imagine that why this kind of timescale pops up. If you have some kind of different kinds of eigenvalues, then 1 over q to the logarithm should be the right one, which just cancels with epsilon. If you have some multiplicities in your Jordan blocks, you need additional logarithmic times, so which you need to run through the Jordan block. Okay, the good thing is this is already very good. First of all, this profile which we have here does not depend on in which p you measure it. It's universal in this sense. It is it depends on very few things. In fact, it depends on the rate, so on the real part, the smallest real part of Q, and we have some multiplicities appearing here, and we still have here this kind of omega limit set, which is of course not nice to evaluate. However, under generic conditions, we can simplify this. Okay, maybe one additional point here. Of course, if you talk to practitioners, they always ask for errors, and we can give errors. So if you look at the distance between, if these things converge, and if you look at the distance between your normalized system and the profile, you can say that it essentially behaves like e to the, and then in the exponent, you have your spectral gap. You have a renormalized spectral gap. So we have some kind of a power of epsilon, which could be better, but nevertheless, this is precisely what comes up. We cannot make it really better. Okay, so another point is we can make it even more beautiful, this kind of result, because these omega of x are not nice actually. So what we can do is we can express the convergence, so the conditions of the convergence in terms of the vectors v, which appeared in this in this asymptotic expansion of the eigenvectors of Q. And they are nice in the sense that so this is a vector of the real eigenvectors, and here we have the real parts and the imaginary parts of all the complex generalized eigenvectors. They have to be orthogonal, and you have some condition on the norm of the real part and the imaginary part. So if this is matched, and you have to prove this, unfortunately, with the help of this kind of omega limit sets, then you get the convergence to a profile. And the profile is even nice. It doesn't have any kind of these strange rotations anymore, because these kind of rotations, if you have non-resonance, they approximate the vector densely 1, 1, 1, 1, 1. And what you get is this kind of profile. So this means you have an exponential profile, and we have, in terms of the parameters of the system, some kind of constant. In fact, it's nothing but a constant. Of course, everything depends very sharply on the initial condition. All right, so, but what happens if we don't have this? And this is, of course, the general case. The generic case is that you don't have this. You can show that you still have an infinity zero break. You have some kind of weaker notion. And this tells us that, well, this thing does not have to converge anymore. But nevertheless, if you send R to infinity, then you have R to minus infinity, you have minus infinity because you're renormalizing here. So you're far away. And as soon as you send your R to infinity, then it gets zero. So you have still this kind of infinity zero break. And this is what should be expected to be seen in simulations. All right, of course, Wasserstein says that the moment should follow, and they follow. Of course, if you go to minus infinity, so first of all, you go to epsilon to zero, you're asymptotic, and then you go to R to minus infinity, then you are far away. But if you go forward, you just converge abruptly to the right moment. So the P's moment, and this can be any kind of P moment which is finite. Okay. All right, examples. First of all, if Q is symmetric, then things are nice because Q can be diagonalized, and it's a gradient system, and you have a profile, and you can write down the profile explicitly, and you have all the error bounds which you would like to have. So it's a good thing. It's very smooth. However, physicists don't like if mathematicians just choose the examples. So what about the linear oscillator? And the linear oscillator is, of course, highly degenerate. It just gives you this kind of, you have a pendulum, which is no long elongation. But of course, you should not make the error to perturb everything everywhere, but you should only perturb the position. So you have velocity and position, and you should only perturb the position, which makes the problem highly irregular. And then you can just distinguish between different kinds of regimes. You have overdamping if the friction parameter G is large. You have critical damping if this is zero. And so it means if the eigenvalues are hardly real. And then you have subcritical damping, and this means that you have real parts. So you have imaginary, you have complex numbers. So if you do this, we have done this, everything is really carried out in detail. It's rather technical, but nevertheless, it's hopefully quite useful. If you have overdamping, then we have real eigenvalues. And real eigenvalues, you have a good logarithmic time scale. We have the profile, which can be written down explicitly. And our results tell us that this kind of distance behaves like epsilon times, and here we have the profile, and we have an error which is actually quadratic. So this is the best thing we can have here. If we have critical damping, we get the same. We have two cases. First of all, repeated eigenvalues. And this is the same case as in the overdamping. This means you have profile cutoff. And the one thing is, if you have one Jordan block, and then we have multiplicity 2, and then we have to use an additional logarithmic term which comes here. So you lose a little bit in the error term. You don't see it actually in the original, only maybe in the friction term below here, but nevertheless, in epsilon, you only see it in this kind of logarithmic term. If you have subcritical, there is no profile. So there's no way to get it, and we just do it by contradiction. If you assume it, then we just run against the subcriticality. Okay, you cannot do this. And on the other hand, we can write down explicitly this kind of orthogonality condition. All right, so I'm already almost at the end. So the last example are it's n oscillators, all coupled. You have the velocity and you have the position, and you have put them in a chain. So this is a very classical example, and only the ones at the borders are exposed to the noise. So this is highly irregular, and the thing that this thing should have an invariant distribution, and you should have some kind of cutoff is not clear in advance. And if you write down the system in the PQQ coordinates, it's horrible. Q has this kind of shape. It's not nice, but we can check it numerically. There is never a profile, but we wanted to see how far it is from profile. So here are numbers. We don't want to talk about this. But if you look at this, you can calculate how far the main vector is from the orthogonality condition. And if you compare the real part and the imaginary part, you can see they are different. And if you look at the orthogonality condition, it's almost matched, but it's not matched. You can see that there is an absence of a thermalization profile. However, we have the zero infinity break for the moments, and we have the sharp decline for the normalized Wasserstein distance. All right, thank you very much. Please, questions.
Well, thank you very much, Michael. Are there any questions from the audience? Perhaps some students, perhaps Andres Angel, I don't know.
I hope I can see any picture because I just lost the picture.
Are you showing a picture now, or?
Okay.
We're just seeing the last slide. That's it.
Okay. So.
Bueno, pues si no hay preguntas, entonces no queda sino agradecerle a Mijail otra vez. Okay. Y recuerden que nos vemos el próximo jueves. Vamos a tener una charla ya les cuento. Déjenme revisar acá mi agendita. Listo. El próximo jueves va a ser el 1 de octubre y vamos a tener la charla de Sebastián Hurtado de la Universidad de Chicago. Entonces, pues nada, están todos cordialmente invitados y de nuevo muchas gracias, Mijail, por tu tiempo y por la charla.
Listo. Gracias. Que estés muy bien.
Adiós. Chao.
Chao. Chao.